Hello dear friends, am I audible? Very good morning. Welcome to one and all. Yeah. Hi, hi Aryan Kaurav, very good morning. CSE Vengideshan, very good morning. Welcome to one and all. Welcome to this session of marathon series, the Maha Marathon series, where today I'll be talking about data structures. So let us start with the next session of the Maha Marathon series, where I'll be taking up problems and concepts of data structures. Okay, sir. Very good morning, Samata. Very good morning. So, and we also have this particular Maha Marathon series for all the branches, my dear friends. Here in this channel for E, EC and electrical and CS, and in other channel, other YouTube channel, we also have this marathon series going on for civil and mechanical students, right? And there is one mega workshop which is conducted by Abhinav Negi sir on 15th January for 2024 aspirants. You can join this live on 15th Jan. Don't forget, okay, at 12:30 p.m. Right? The 7 success mantras for from a beginner to a top. So that that is conducted on 15th Jan. And this is about me. Hope you all know about me. Myself, Sridhar Dhulipala, I am having 20 plus years of teaching experience, and I am associated with BYJU'S from almost 2 years. And initially we worked on this particular project called recorded GATE content, first of its kind, and we created visualized animated content for you, first of its kind. And under BYJU'S Exam Prep app, the category name you can note down, learn with video lessons, where you can find all the recorded lectures which were recorded by me. Okay, like I recorded engineering mathematics for all branches for computer science exclusively, the following subjects: discrete mathematics, C programming and data structures, algorithms, right? So with that introduction, let me start with today's session. And I'm sorry, it may be mentioned algorithms. One second. Okay, a small twist in the story. Okay, so its dynamic change happened. The data structures part 1. Right. So the topic which I am going to discuss under data structures are, in today's class I will be taking up this arrays and trees, and in the next session, that is tomorrow's session, we will see the topics like linked list, stacks and queues. Because here Kaustubh Nageshwar, hello sir, good morning to one and all. Good morning to one and all, sir. So let us straight away start with the problems. An array, see, it is not a C array, sir, it is a general array we are talking about, is stored in memory. Each element of array occupies 2 bytes. Starting location of the array is 1000. What is the location of A0? That is the question. What is the location of A0? That is the first problem, sir. Please answer the question. Option A, option C, different answers you are getting. See, my dear friends, when array is stored in say location LU kind of things, in this particular case the formula for location AI is given by the base address location plus the location you want minus the starting index into size of the array, where alpha is the base address, I is the current index which you want to find, L is the lower index and U is the upper indexer. Am I clear? And K is the size of the memory taken by each element, where K is the size of each element. Okay. So once you have everything ready, 1000, I is 0, the lower index is -5 into 2, which is 1000 into 5 into 2, which is 10,010. What I done? 1010. So the correct answer for this problem is option C. The correct option for this problem is option C, my dear friends. Hope you understand. Any doubts, please let me know. If you have any doubt, please let me know. The next problem. See, very good. I think Saubhagya Nayak, you done a good job, and Kaustubh Nageshwar, as usual. Vengideshan, please verify this. My voice is little low. Is it okay now? We do one thing. Okay, let me adjust my voice. Hello, hello, hello. How is my voice now? How is my voice now? Is it better? How is my voice now? Is it better? All clear? Fine. Hello, hello, hello. The next problem. An array is stored in memory. Each element of array occupies 2 bytes. Low. Is it still low? Okay, meanwhile you try. Let me adjust the volume then. Hello, hello. Hello, hello, hello. I think now it should be okay for all of you without any trouble, hopefully. Now the voice, I think, is perfectly fine. Yeah. Right, sir. Now look here, same story, but here he's just asking third element. He's just asking third element. See, when you want third element, you don't need to use any formula. Starting location is 1999 and first element, every element is taking 2 bytes. Okay, so the next element is at 2001. This is first element, this is second element, and the third element is 2003. So option B is the correct answer. Most of you given correct answer directly. Am I clear? Wonderful. You can also extend this idea for, what do you call this? Two-dimensional arrays also. But for two-dimensional arrays, we need to understand this like row major order, yeah, column major order. Whether you are storing it in row major order, yeah, column major order. Am I clear? So row major order means row wise you are going to store the elements. Column major order means first column, second column, like this you are going to fill the elements. What about this row major order? Please answer this question, my dear friends. The location of ith row jth column element when it is given in row major order is given by alpha I minus L1 into number of columns plus J minus L2 into K. Here this is your L1 U1 and this is L2 U2, my dear friends. If it is column major order, the location of ith row jth column element would be alpha plus J minus L2 into number of elements, okay, or number of rows plus I minus L1 into K. So accordingly you use the formula to get the required answer, because here it is mentioned that it is stored in row major order. Each element is occupying 2 bytes. So you want location of 0, 10 where L1 is minus 5, L2 is 5, everything is readily given. Use the formula to get the required answer, my dear friends. Use the formula to get the required answer, my dear friends. Okay. Now what happens to this location of A, 0 and 10? Because starting memory location address is 1000 plus now you are in, I mean 0th element means 0 minus, how many you have to complete? Starting fellow is minus 5, 0 minus minus 5 into how many columns are there? See, U2 minus L2 plus 1 give you number of columns. Number of columns is U2 minus L2 plus 1. Number of rows, if you want to find it, U1 minus L1 plus 1. So it is actually 16. It is actually 16. Then J is 10 minus L2. L2 is 5 into 2. So this is the formula for location of A, 0, 10. Just use the formula to get the required answer. 1000. Now it is 16 5s, 80. 80 plus 5, 85 into 2 bytes, which is 170. 1170 is the required answer, which is option D. Most of you are doing perfectly fine. Okay, nice. No issue at all, right? Very good. See, sometimes you get a question and most of the people always have confusion whether it is a problem from CS question, so problem from arrays or problem from engineering mathematics or general logical problem. See, this happens especially for computer science students. You can have question which can be related to almost all the topics. Now you can take it as a topic from, engineering mathematics, or you can take it as a topic from arrays, or you can say common sense problem. It's a common sense problem also. With the common sense also you can solve it. Okay. See, when you want to solve it with common sense, just take these numbers like 2, 3. That is how generally people solve it. See, the sum of elements of the array. It's actually Vij is equal to I minus j, means it is a skew symmetric matrix. It is actually a skew symmetric matrix. For those who know that sum of elements in a skew symmetric matrix is 0, directly answer is 0 for that. Okay. Sum of elements in a skew symmetric matrix is what, sir? Is 0. So with that property you directly get the answer. That is the best way to handle this particular problem. Of course, we also can do this like, you can take a simple 3 by 3 matrix and check what happens. I minus j means main diagonal elements are 0. Here 1 2 means minus 1, 1 3 is minus 2, 2 1 means 1 and 2 3 means minus 1. 3, 1 is 2, 3, 2 is 1. So obviously from this you can take the matrix, then you add up all the elements, then sum of all elements is, sum of elements will be equal to what, sir? 0. Like that also you can solve it. Am I clear? If you add all the elements, you are going to get 0. The next one. Sometimes we can get such general problems. Even these are all logical kind of questions only, my dear friends. Let A be an array containing n integers in increasing order. So here we are having elements in increasing order, my dear friends. Maybe like 3, 5, 7, 14, 19, 23. There is no need of like, every time you should add increase only 2 elements like that. It is increasing sequence. We have some increasing sequence like this, increasing order given. The following algorithm determines whether there are two distinct numbers in the array whose difference is a specified number or not. Whose difference is a specified number or not. So that is what it is going to check, my dear friends. Suppose it is checking that the specified number difference between two numbers, two distinct numbers in the array is 9, you are checking. Okay, suppose assume that this is your array and you are checking that the difference is 9 or not. You are checking difference between two fellows is 9 or not, you are checking. So in this there is some missing part. We have to identify the missing part. We have to identify the missing part. Aryan Kaurav says B answer. Very good. Simple. Nice. So here what is happened, sir? Here what is happened? We started with I is equal to 0 and j is also started here. J is also started here. While j less than n, you are continuing. Now for what condition you have to move j? Now what happens if aj value and ai is equal to s, required number, you break it. Now for what value you increment I? See what we do, sir, we fix I and we move j. Suppose the difference is less than 9, this j need to move further because already difference, because they are all in increasing order now, the difference is less than 9 means maybe with the next number the difference may be equal to 9. So that is the idea. So when the difference between aj and ai is less than the required sum, you move j. Suppose if it is more means if you move j further, it will be more than that only. So if the difference aj minus ai is greater than s, you can't get that particular sum by moving j here. So what we do, we just move I in that particular case. So this is the case where we check whether aj value minus ai value is less than s, then you move j further. Suppose in this case, this else part correspond to what condition? aj minus ai value is greater than s, because for equal to s, we break and you come out of the loop. Am I clear? So that is the logic, my dear friends. So what actually happened, if you want sum is equal to 9, first you start with both equal to 0 index. aj minus ai is equal to 0 because it is less than 9, j is moved. 5 minus 3 is 2, which is less than 9, j is moved. 7 minus 3 is less than 9, j is moved. 14 minus 3 is 11, which is greater than 9. So j stops here, I moves here. Now I moves this else part. Now 5 minus 4, 14 minus 5, how much, sir? 14 minus 5 is 9. You got the required sum and you come out of the loop. So this is what happens in this particular situation, my dear friends. Very, very simple problem. See, sometimes such simple logical questions they'll ask you. Keep your mind open. For this, you don't need any special practice, my dear friends. You just need to understand the array and the logic. It is called semantical problem. Just logic oriented question. Because what he want, he clearly mentioned. Am I clear? Even in interviews, you can get such type of questions. These are general puzzles. Right? So the answer, I think you understand. Right? Yeah, please answer this. A very popular question. B is the correct answer. Yes, Aryan Kaurav. B is the correct answer for this. Yeah, next problem. The next problem. No answers? Difficult question. Leaves S unchanged, Venkideshan? Guessing or what? See, suppose you are given an array and a procedure reverse which reverses the order of elements between the positions I and j. What does the following sequence do? See, you don't have to worry about it, sir. Just take some elements, random elements, say 1, 2, 5, let us take it. 1, 2, 3, 4, 5, say 6 elements, let us take it. Guessworks, you should do it for GATE. You should leave it for GATE examination. Here we should do the complete problem. Now what you are doing? Reversing 1 to n. See, this 1 to n means the given first step will do what, sir? It will reverse all the elements. So what it will do? 6, 5, 4, 3, 2, 1. The second step, it is going to reverse from 1 to 5. 1 to 5 you are going to reverse. That is 1 to 5 indices now you are going to reverse. That is 2, 3, 4, 5, 6. Now 6 to this is as it is. Now here you are reversing 6 to 1, 6 to n. That is last element only actually. If you have more element, then you will understand better. Because here I said fine. Minimum if you keep 10 elements, then you will understand better. No problem. Here also we can do it. Reversing this will give you what's a 2, 3, 4, 5, 6 and 1. Now what happened? This S is rotated or left unchanged. Unchanged is wrong. Reversed all the elements. It is not reversing all the elements. That is also wrong. Now, are you rotating S by left or right, sir? Rotating S by left or right? What is happened here? Rotated. Acha, option E is not hidden. Reverse all the elements, sir. Option D is reverse all the elements. Option D is reverse all the elements. See, when one is shifted right to one position, this is where it is. So 2 positions means this is here. 3 positions means this is here. 4 positions means 1 will be here. 5 positions means this is here. See, what happens? The elements are rotated right by 5 positions. Elements are rotated right by 5 positions, my dear friends. So option B is the correct answer. See, these are the two popular important concepts. If you reverse the entire array, then you reverse from 1 to k and reverse from k plus 1 to n. It will rotate array right by k positions. Suppose this reverse part, if you write at the end, if you write the reverse part at the end, what happens? Rotate array left by k positions. When this will happen? First you have to reverse from a to 1 to k positions. Then you have to reverse from k plus 1 to n positions. Then reverse the entire array. When what happens? It will be rotated by k positions left. See, just the position of this will decide whether you are rotating by right, you are rotating by left, my dear friends. Just remember this very important logic for rotating an array by left, yeah, right, my dear friends. Hope you understand. Very good. Now we start with the trees concept, sir. We are starting with trees concepts, my dear friends. The concept of trees. Okay, so we'll try to spend some time, quality time on this particular tree properties. Hopefully you all are experts in tree properties. So let us see how good you are with tree properties. They're all very simple questions, straightforward questions, expecting answers from you, my dear friends. Trees. The next problem. A binary tree rooted is, a binary tree In a binary tree, root node is at depth 0. Sorry, in a binary tree, root node is at depth 0. The maximum number of nodes at depth k. Because sometimes what people do, depth is taken at depth of root node is taken as 1. Generally, depth of root node is taken as 0. That is, the levels and depths are to be understood properly, my dear friends. So here in a binary tree, what happens? We have this kind of binary tree, for example. So generally here this level, some people start levels from 0, some people start level from 1. So instead of level discussion, it is always better to discuss in terms of depth and height. See, generally this is depth 0 here, depth 0 here, depth from root node it is 1, it is at depth 1, it is at depth 2, like that we can continue, my dear friends. Okay. So height also will be the same, sir. Height will be depth of this particular node we are going to do. Height will be the same story, my dear friend. Height will be the depth of that particular node. Am I clear? Height also we can define in the same manner. Hope you understand. So what is the correct answer for this? Venkateshan says D. Kaustubh Nageshwar says B. See, my dear friends, root node is at depth 0. So at depth 0, how many nodes are possible? 2 power 0 nodes, that is 1. At depth 1, maximum how many nodes are possible? Maximum 2 nodes, that is 2 power 1, 2. Similarly, at depth 2, how many nodes are possible? At depth 2, 2 power 2, that is 4 nodes. So similarly, at depth k, 2 power k nodes are possible, sir. At depth k, 2 power k nodes are possible. 2 power k is the answer. Maximum number of nodes at depth k is 2 power k. Very good, Mr. Kaustubh as well as Venkateshan, your answer is wrong. It's not -1. It is just 2 power k. Next question. The height of binary tree is the maximum number of edges in any root to leaf path. See, this definition generally they mention and they'll ask the question. Because some people define heights also in different way. Am I clear? So here I define height as, what is height? For example, what is height of this particular binary tree? Can you tell me what is the height of this particular binary tree before answering the question? What is height of this particular binary tree, my dear friends? What is height of this particular binary tree? Height is 2. Height is 2 here. Now he says, he defined height. Now he says the minimum number of nodes in a binary tree of height h. Suppose if the height of binary tree is mentioned, height is h, then what about the minimum number of nodes? Minimum number of nodes for a given height. Okay, most of you answered C, C, B. Someone says B, someone says C. Okay, see, you just see this example, sir. Here height is 2. See, we get minimum number of nodes when it is a degenerate. When it is a degenerate binary tree, like this. So here the nodes would be what, sir? 3 nodes we are having. So minimum number of nodes would be h plus 1. Minimum number of nodes would be h plus 1, my dear friends. That happens when it is a degenerate binary tree, my dear friends. That is left skewed or right skewed. That fellows will have, okay, this minimum number of nodes. C is the correct answer. Very good. What about maximum number of nodes in a binary tree of height h? What about maximum number of nodes? What about maximum number of nodes? See, maximum number of nodes are possible when all the levels are completely filled. See, we get max nodes. Maximum nodes means what should be the condition? All the levels are completely filled. All the levels are completely filled. When all the levels are completely filled, we get maximum number of nodes, my dear friends. We get maximum number of nodes. So people are saying B answer, very good, because first level, second level, third level, or level 0, level 1, you can say like that. This is what happens, my dear friends. For example, if height is equal to 3, this is the maximum number of nodes. See, height 0, maximum is 2 power 0. Height 1, 2 power 0 plus 2 power 1. Height 2, 2 power 0 plus 2 power 1 plus 2 power 2. Like that, if height is h, it should go up to 2 power h, my dear friends. And which is simply a geometric progression. Okay, so what is the answer for this? 2 power h plus 1 minus 1 by 2 minus 1. And that is nothing but 2 power h plus 1 minus 1. Please practice this with different numbers, my dear friends. Practice this with different numbers. Okay, so by putting height is equal to 3, you practice height is equal to 4. Practice this always with h values. Suppose if h is equal to 7, if height is equal to 7, what about the maximum number of nodes? What about the maximum number of nodes? For height is equal to 7, what is the maximum number of nodes? For height is equal to 7, what is the maximum number of nodes? Very good. 256 minus 5, 255. See, always practice with numbers. See, write down the standard formula and practice with different numbers. You keep h is equal to 1. See, for that you don't need to take any books. You don't need to take any book. So, someone want to make you fool, they'll create some, test series with all these h values only. So, standard rule, you know it, then automatically all this will follow clearly, my dear friends, right? The next one. The height of a binary tree is maximum number of edges in any root to leaf path. Okay, I know it. Fine, thank you. The difference between maximum and minimum possible number of nodes in a binary tree of height 9 is equal to what? Please answer the question. Did I ask very difficult question? Bad question? Very good, Saubhagya. Vengideshan, please check your answer. Aryan Kaurav, very good, Nana. Height is equal to 9. What about maximum nodes? What about minimum nodes? He is asking difference. Maximum nodes is 2 power 9 plus 1 minus 1. Minimum nodes h plus 1. That is 1023 minus 10, which is 1013. Okay. See, sometimes this type of difference questions they can ask you. Be ready for that. That's it. Okay. Nice. Questions changed. The height is same. The minimum height of a binary tree having n nodes. So it is a binary tree having n nodes. What is the minimum possible height, my dear friends? What is the minimum possible height? Aryan Kaurav says B. Hope you remember that. See, the minimum height is possible when all the levels are completely filled and last level is filled as much as possible. That is the story. So we take that the situation of that n as the maximum number of nodes with the given height. Then what happens? We'll get the minimum height, my dear friends. Simply the minimum height is given by okay, because 2 power h plus 1 minus 1 is the maximum number of nodes for a given height. Okay, so when you have maximum nodes for a given height, okay, see, sorry, when you are having maximum nodes for a given height means more nodes are filled in each level. So this is the situation we are actually solving for. So this is the idea, my dear friends. So solve this. 2 power h plus 1 is equal to n plus 1. That means h plus 1 is equal to log n plus 1, or h is equal to log n plus 1 minus 1. So this is about the minimum height of a binary tree having n nodes, my dear friends. Wonderful. And what about the maximum height, Babu? What about the maximum height? What about the maximum height? So maximum height for a given number of nodes is n minus 1. Am I clear? So this is n minus 1. See, n nodes you are having, maximum height is possible when you are having single node in each level. So suppose you are having 3 nodes. What is the height? Height is 2. Always it is 1 less than the number of nodes. Similarly, practice this with different numericals, my dear friends. Wonderful. The maximum number of leaf nodes in a binary tree having n nodes. The next question. The maximum number of leaf nodes in a binary tree having n nodes. Very good. Maximum nodes, maximum leaf nodes when possible, sir? When you can get maximum leaf nodes? Maximum leaf nodes are possible when you are having minimum height. The height is minimum for the given number of nodes. See, for the given number of nodes, what is the minimum height, my dear friends? For the given number of nodes, minimum height is given by, just now we done, which is log n plus 1 by 2. Just now we solved this one. Minimum height. This is nothing but log n plus 1 minus log 2. Yeah, it is same as log n plus 1 by 2. There is one more way of, yeah. So log n plus 1 by 2. This is the minimum height, my dear friends. So for this, in this particular height, this is the height. Maximum nodes, number of nodes in this height. That is, at this level, how many nodes are there? Or at this depth. Okay, nodes at depth, h is equal to log n plus 1 by 2. At this depth, how many nodes will be there? Which is equal to 2 power h. That is nothing but 2 power log n plus 1 by 2. These two get cancelled and you get n plus 1 by 2, my dear friends. So that is the idea, my dear friend. Maximum number of leaf nodes in a binary tree having n nodes. See, one way of doing this is, you can just draw an example by taking n is equal to 3 or 4. There you can check and compare the answers, my dear friends. See, for example, for a given number of nodes, what can be the maximum number of leaf nodes when you can have, sir? That you can check it here. So here 7 nodes you are having. Leaf nodes are how many? Leaf nodes are how many? Is 7 by 2 satisfying? 7 plus 1 by 2, which one is satisfying? With that example method also you can solve it, sir. With example method also you can solve it. Yeah, like that we can verify, my dear friends. Hope you understand. Next one. The height of a binary tree is defined to be maximum path length from root to any leaf node. Very good. The maximum number of leaf nodes in a binary tree of height 19 is equal to. What about the maximum number of leaf nodes in a binary tree of height 19 is equal to? Very good. N plus 1 by 2. See, if you know the formula, just now you can see in the formula, so you can easily answer it. N plus 1 by 2, that is 19 plus 1 by 2, which is 20. Am I clear? But the same problem when it comes in examination, the previous problem may be OS problem, or previous problem may be a computer network problem, and after this you got this particular problem, your mind should work in the same manner. Please remember that. The next one, interesting result. In a binary tree, the degree of a node is the number of children, number of its children. Okay, number of children the node is having. So he's just defined what do you mean by degree here. In a binary tree, the degree of a node is the number of children. A binary tree, the number of internal nodes of degree 1 is n1, and the number of internal nodes of degree 2 is n2. Then number of leaf nodes in the binary tree, that is number of nodes of degree 0 is equal to how much? How many nodes of degree 0 are there? C. Aryan Kaurav says C. The very popular relation between 0 degree vertices and internal nodes of degree 2. D. See, this is a popular relation between N0 and N2, Babu. Please remember, I'll derive this now. I'll show you how. See, remember, this is the most important result. Please remember. How? Let me explain. Let me give you the proof for this. Are you ready for the proof? Right. Now look at this, sir. Suppose n is the number of nodes. We are having, we don't know how many leaf nodes are there. Let us say n0 is leaf nodes. N1 is nodes of degree 1 and N2 is nodes of degree 2. It is a tree. Therefore, number of edges will be n minus 1. Number of edges will be n minus 1, my dear friends. Number of edges will be n minus 1. Correct? So, that is E is equal to n0 plus n1 plus n2 minus 1. Now, when you consider the number of edges in terms of degrees here, leaf nodes contributing degree 0, nodes of degree 1 are having only one children, so they contribute degree 1, and nodes of degree 2 contribute 2 degrees. Here they are all only, we are talking about children means only out degrees. So here we should not take twice the number of edges. Here we are only talking about out degrees here. We are only talking about out degrees. So in a directed graph, the out degrees, sum of out degrees is equal to number of edges. So that is the idea. Here number of edges will be equal to, see, the leaf nodes are not giving any edges. So they'll give you 0 edges. So 0 into n0. Nodes of degree 1, they have children, 1 children each. So n1 nodes means n1 edges it is going to give you. That is 1 into n1 edges it is going to give you. And nodes of degree 2, they are having 2 children means they are going to give you 2 degrees. That is 2 edges they are going to give you. That is 2 into n2. So this is the value of E, my dear friends, which is n1 plus 2n2. See, this is also number of edges. This is also number of edges. Just add them. That is equate them or compare them. Okay, so from 1 and 2, because 1 is same as 2, we get n0 plus n1 plus n2 minus 1 is equal to n1 plus 2n2. These two fellows cancel. Therefore, you are going to get n0 is equal to n2 plus 1. Please remember this very interesting result about nodes of degree 2 and nodes of degree 1 in a binary tree, my dear friends. Nodes of degree 2 and nodes of degree 1 in a binary tree. Please remember, my dear friends. Hope you understand. That is the idea. So always remember this formula. They ask this question number of times in GATE examination. A very popular, important formula. Remember that. Answer this question now. Now people are answering very quickly, because I asked number of leaf nodes, that is number of nodes of degree 2 plus 1. How many nodes of degree 2 are there? 10 plus 1, which is 11. Now you don't have to solve the entire story, sir. Just note that idea, you will get the answer. Super. Very good, Saubhagya. Very good, everyone. The next one, the number of binary trees with 4 unlabeled nodes. Number of binary trees with 4 unlabeled nodes. So C is the answer for this. Very good. 14. The number of binary trees with 4 unlabeled nodes. See, my dear friend, number of binary tree with n unlabeled nodes is given by Catalan number. It is given by Catalan number. And the formula is Cn, we denote it, which is 1 by n plus 1 into 2n Cn. So those who do not know, note this, my dear friends. The answer for this would be 1 by, because you want 4. So C4 is 1 by 5 into 2 into 5, 10 C5, which is 1 by 5 into 10 factorial by 5 factorial into 10 minus 5 factorial. So simplifying, you're going to get this 14 answer. But sometimes they can ask you number of binary trees with 4 labeled nodes. If they are labeled nodes, what about if the nodes are labeled? If the nodes are labeled, or let us write it as general formula so that you can remember this for a long time. N labeled nodes, in that particular case, the answer would be Cn multiplied with n factorial, because the n labeled nodes can be arranged among themselves. the nodes can be arranged among themselves in n factorial ways. Because of that, into n factorial will come. Oh, sorry. I was in different. Yeah. Sorry, sir. Sorry. Answer was 14. Sorry for that. Who is that? Yeah, Aryan Kaurav. No, right, Nana. 8C4 only. Yes. Yes, you are correct. Perfect. So when it is labeled nodes, you need to multiply with factorial, otherwise just that Cn, Catalan number. There is one more interesting question which they can ask you is strict binary trees. See here, strict binary tree means degree of node is either 0 or 2. There are no nodes of degree 1. Hi Nishu. There are no nodes of degree 1 here, sir. The degrees are either 0 or 2 only. Such fellows are called strict binary trees. See, for number of strict binary trees with n, the formula is with n nodes, the formula would be difficult to remember because you have to write Cn minus 1 by 2. So what we do here is internal nodes. So we give this formula for internal nodes. So when you know number of internal nodes, then you can say how many strict binary trees are there. And here n should be odd because n is even, then that is not defined. So for strict binary trees, n should be odd. Then you can define like that. N should be odd again. Otherwise, for number of internal nodes it is having, we can give the answer. If it is having n internal nodes, okay, if it is having say number of strict binary trees, if we ask, strict binary tree means degree of each node is either 0 or 2 with k internal nodes. Internal nodes is very important here, is given by the formula Ck, my dear friends. Catalan number, same Catalan number. That is 1 by k plus 1, 2k Ck. Hope you understand. Please remember this. So please tell me if it is having 3 internal nodes, how many strict binary trees are there? If it is having 3 internal nodes, how many strict binary trees are there? Please answer this question, my dear friends. Five. Because C3 is 1 by 4, 6 C3. Okay, that is 20 by 4, which is nothing but 5. 5 is the answer. And there is one more question which is called number of binary search trees. Number of binary search trees. So what is the answer for this? These 3 formulae which I given are very, very important, sir. Possibility is there. They can ask you in examinations regularly. So please do remember, very important formulae. Yes. This is also equal to Catalan. Here distinct keys, it's not like unlabeled. Binary search trees, you all know what is a binary search tree. Okay, so the keys are having definitely some order, some relationship. So number of binary search trees with n distinct keys. If it is n distinct keys, then directly formula is Cn, Catalan number. Always formula 1 by n plus 1, 2n Cn. So directly Vengideshan, Nishu Kumar, Saubhagya Naik, all of you. Oh, who is giving C answer, Babu? Babu Saubhagya C kadu. 5 keys. Then it is 42 binary search trees are possible. 42 binary search trees are possible. So remember these 3 numbers. For binary trees, Catalan number. For unlabeled, it's not labeled. Unlabeled, it is Catalan number. Labeled means you have to permute those nodes, my dear friends. So into n factorial you're going to get, right? And if it is a strict binary tree, we are having Catalan number for that internal nodes. How many internal nodes are there? For that answer you're going to get it. Whereas for binary search trees, number of keys, Labeled only, that labels only can give you. With labels only we'll get binary search tree, sir. Otherwise how can you define binary search tree without any labels? That is, binary search tree without label is a illegal story. So obviously it is labeled only. Directly CN is the answer. Directly CN is the answer. Now let us take up some problems, very interesting problems. I think you're all experts, but otherwise let us do this. Which of the following sequence denote the post order traversal sequence of the below tree? Post order traversal sequence of the below tree. Very good. Super. Okay. See, generally for pre-order, post-order, we should have the recursion in mind. Then directly writing is very good practice actually. Post-order he want. So post-order if you want to write it. Post-order means what, sir? Post-order means first left subtree, then right subtree, then finally root node. Left, right and root node. So what we can do is, you can think this in your mind. First you are going to complete the left subtree, okay, in the post order method. So again for the left subtree, first complete the left subtree in the post order. Again here the left subtree you have to complete it, that is first G is completed. Then its right subtree not there, so left right completed, then root node. So C is traverse. So the left subtree is completed, then you move to the right subtree of this. Right subtree single node is there, happy situation, print that. Then left and right are done, then you print the root node, my dear friends. Then what happens? The left subtree is completed, move to the right subtree. Right subtree also you have to traverse it in. Right subtree also you have to traverse it in post order. Post order means what? First left subtree in this. In this first left subtree, that is only single node, so directly you can trace it or directly you can visit that. Then right subtree is not there, so then you have to visit the root node, which is E. Now left and right are completed, finally visit A, my dear friends. See here, without writing any of these circles and all, if you can draw that post order, then it is wonderful, my dear friends. Without doing anything, that post order thing if you can do directly in the mind, then it is wonderful. Of course, people are very much interested in this kind of methods where we know we use this link method. You create these links like this, and they traverse. We call it as a Euler walk or whatever walk, sir. So we start walking from here. So every node is visited 3 times, left, middle and right. Right, middle, left, left, middle, right, middle, right, right, up. So with this also, what they do, they use that left, middle, right, or they use the numbers. When you visit the node on the left, you can call it as ones, middle you call it as 2, right you call it as 3. For every node you will have this 1, 2, 3 numbers. For every node will have this 1, 2, 3 numbers. Am I clear? This is 1, 2, 3 for this. This is 1, 2 and 3 for this, like this. So you can start walking from here. You can start walking from here. So if you want post order traversal, you just start walking here. And you have to print whenever you get 3, sir. You just walk like this. And you have to print all the 3's in this order. When you get 3, you have to print the node. Now you got the 3, so G is printed. Next continue. Next you got 3, C is printed. Then again you continue. Continue. Now you got 3, D is printed. Continue this. 3, B is printed. Continue this. 2, you got 3, F is printed. Continue. You got 3, E is printed. You got 3, A is printed. Like this. So with this numbering schema also you can write the post order, my dear friends. You can write the post order. But as I told you, without using any numbering schema, directly reading the tree, if you can answer this, then it is wonderful. So please write down what is pre-order and in order for the same tree, my dear friends. What is a pre-order and in order for the same tree? Please write down, complete that. What is pre-order? You can write for pre-order all once, you can write down, sir. For pre-order it is root node, left subtree, right subtree. Yeah, torpedo, very good. So pre-order means first you traverse the left subtree, first you visit the root node, then left subtree in the pre-order manner. Again here root node, left subtree. Again root node, left subtree G, done. Now entire left subtree root node is completed, then right subtree only D is there. Now here right subtree in pre-order, first E then F. So A, B, C, G, D, E, F. A, B, C, G, D, E, F. D, E, F na, not F, E. Babu, why F, E, sir? Acha, see pre-order, I think you made some mistake. After this E, F, because pre-order means first E then F is listed. First E then F is listed. E, F. Torpedo, your in pre-order is wrong. Please check that. After D, it is E and F. Hmm. Now, what about in order, my dear friends? What about in order, my dear friends? In order means what? In order means first left subtree, then root node, then right subtree. So first you have to traverse left subtree. See, you can do twos, all twos in the order, that will give you the answer. But first left subtree, again left subtree is there, again left subtree. So first G will be printed, then root node C will be printed, right subtree is missing. Then B is printed, then right subtree D is printed. Now left subtree completed, then the root node. Again the right subtree in order. In order means first left subtree, then root node, then right subtree. So it is G, C, B, D, A, F, E, my dear friends. G, C, B, D, A, F, E, my dear friends. So that is the answer. So these are the pre-order, in order and post orders, my dear friends. The problems on this pre-order, in order, post orders are very, very important for GATE point of view, my dear friends. They are very, very important. See, in the worst case, you can draw this particular diagram. With that also you can always write. So there is a very little chance of doing mistakes in this problem, my dear friends. Now this is very, very common question. They'll give you like pre-order, in order, yeah, post order, in order, sometimes level order, in order also. From that you have to construct the binary tree, my dear friends. Constructing binary tree from pre-order, in order, post order, in order, etc. Okay, so let us see this, my dear friends. The in order pre-orders are given. Is it correct? In order pre-order only? In order, this is in order and it is pre-order are given. You have to find the binary tree, my dear friends. Can you identify this, Babu? Please try. Okay, is it B? Let us see this. So here pre-order is A, B, D, E, C, F, G, and the in order is this one. This is in order. So in pre-order, the first node is root node. Am I clear? So this is the root node. So the root node will divide the left subtree and right subtree. So for left subtree, this is the in order DBE. For right subtree, the in order is FCG. Now what happens? This DBE, this BDE is actually pre-order. Here I am writing pre-order, which is BDE. And for the right subtree, pre-order for right subtree is CFG. Again continue the same story. This is pre-order, therefore B will be the root for this. So B root means obviously D is the left subtree and E is the right subtree. Here C is the root, and in order that C will separate the left and right subtree. So it is a one word answer, simple story. A, B, C, D, E here, F here, G here. And you just want post order here. What is the post order, my dear friends? What is the post order, my dear friends? See, post order, as I told you, first left, then right, then root node. Am I clear? He is asking post order. So left to right, then root node means first you have to traverse left. So in that left completed, then right completed, then root node. Now left tree is completed. Now move to the right subtree. Again that has to be visited left, right and root node. That is F, G, C, and finally A will be visited. That is D, E, B, F, G, C, A. D, E, B, F, G, C, A. It is option A, na? Some people are saying B. A is the correct answer, I think, right? D, E, B, F, G, C, A. Correct. Option A. Please be careful. See, these problems we should not do mistakes, standard ones, and I think many number of questions are available everywhere. So every now and then you can find problems on this, and they are asking these questions very regularly because the general logic, my dear friends. Okay, so once you understand this logic, then you can think about writing a program for this. All these things you can try later on. See, here they are interested in the logic part. See, once logic is ready, don't think you can go for the next one. That logic you have to implement, na? So we have bigger headaches than that. Okay, so the logics are very, very important here, my dear friends. The next one, the post order traversal of a binary tree is given, and the in order traversal is also given. He is asking height of the tree for this. So you have to construct the binary tree and you have to tell what is the height of the binary tree. What is the height of the binary tree? Three. Now look at this. Now look at this problem, my dear friends. All of you, I want you to see this carefully. See this carefully. Yeah. See here it is post order traversal and it is in order traversal. So what you do is find the last node in the post order traversal is the root node. Last node is the root node and see where is this root node. Okay. So this is the root node in the in order and right subtree just 3 single node. The left subtree in order is this one. This is the left subtree is in order, which is 8, 6, 9, 4, 7, 2, 5. Now actually once you identify the in order, one is in one part, the other fellows are in other part. Sorry, 3 is in one part. Sorry, 3 is in one part. So this part you don't have to worry about it. The not pre-order, post-order. The remaining part is post-order. Post-order for the left subtree. So the post-order for left subtree is 8, 9, 6, 7, 4, 5, 2. Again identify the root node here. What is the root node here? 2. So check 2 will separate the left and right subtree in the in order. So 1 here, 3 here and 2 is the root and right subtree it is 5 and the left subtree in order is this one. Left subtree in order is 8, 6, 9, 4, 7. Now you observe this 2 is done, 5 is in the right subtree, so ignore. For the left subtree pre-order is, what is the pre-order for left subtree? Sorry, post order. What is the post order for left subtree? The post order of left subtree is 8, 9, 6, 7, 4. Again identify the root node here. Again identify the root node and it will separate again. We are having 1 here, 2, 3, 5. Then it is separating 4. 7 is the right subtree and the left subtree in order is 8, 6, 9. Left subtree in order is 8, 6, 9. So once you have this left subtree in order 8, 6, 9, that is 8, 9, 6 will be the left subtree post order. So post order of left subtree is 8, 9, 6. So 6 is the root. So 6 will separate the left and right subtree. So finally you get 1, 3, 2, 5, 4, 7 and 6 will separate the left and right subtrees. 9 here and 8. So with this, Babu 7, what is that? Either 3, 7, too much variation you are giving. Height is what? 1, 2, 3, 4. 4 edges are there. Height is 4. Height is 4 Venkateshan. So you are giving any answer, 7, root node you are telling, fine. No problem. So these questions they can ask you, they can give you pre-order, in order and they can ask you post-order, or they can give you post-order, in order and they can ask you pre-order, okay, or they can ask you height of the tree, or they can ask you one more question like this. Try this then. One more question. Quickly try this. In order and pre-order are given. He is asking number of nodes in the left subtree. How many nodes are there in the left subtree? How many nodes are there in the left subtree? Okay, so very good. So we have in order, this is in order. In order is A, B, C, D, E, F, G, H, I, J, which is in order. Pre-order is this. So in the pre-order, you can identify the first node is root node. So this is the root node. So you can easily separate. G is the root node. Then the left subtree will contain how many nodes? The in order of left subtree is A, B, C, D, E, F, and the right subtree's in order is H, I, J. See, here you don't have to solve the complete problem, sir. Problem is done. The left subtree will contain 6 nodes. That's it. That is the answer. See, sometimes people do the entire story. You need to do the entire story for solving this problem. Are you going to do the entire story, sir? No, right? Clear or not? Please try to understand the logic, Babu. Don't unnecessarily overdo. Okay, that's it. Problem is done. Hope you understand. Hope you understand. Clear? Yeah. Next problem. Next problem. Okay. Now binary search trees. A binary search tree is used to locate number 43. Let us take this problem, sir. A binary search tree is used to locate number 43. Which of the following probe sequences are possible? See, my dear friends, in binary search tree, what happens? You need to identify, because once you taken a number between say 10 and 50, you cannot go beyond 50 or you cannot go less than 10, my dear friends, because in binary search what happens, you are finding between the two values. So that would be the logic, my dear friends. Please remember that. Okay, so because of that, you have to be very careful with binary search tree problems. Now look here, whether this is a probe sequence or not, just keep on constructing that binary search tree, you will understand this. You are searching for 43. Let us see option A. Let us see option A. First you probed for 2. 2 is the root node. And 43 is greater than 2. So you should move to the right subtree. So right subtree you may have 3. That is fine, absolutely. Then it is greater than 3 means right, we should move to the right of this. Then we are having 50. See, my dear friends, the next numbers which you are going to get must be between 3 and 50 only. You can never get any number greater than 50 or less than 3 here, because already you crossed 3. So the number which you are going to get is between 3 and 50 only in the probe sequence. In the probe sequence, it should be between 3 and 50 only. The next one is 40. It is less than 50, fine. You can move to the left. The next one is 60. Because you are already in this particular route, next one is 60 means you can't move to the right of this, because 60 will be right of here. So this is wrong. So this probe sequence is wrong when you are searching for 43. Next, option B. Option B. What about option B, my dear friends? You started with 10, fine. Next is greater than 65, that is fine. So the number should be, any number probes you are going to get must be between 10 and 65. Then you are getting less than 65, fine, 31. Then it should be between 31 and 65 only. Then you are getting 48, that is fine. Then you are getting 37. So 31 and 48, it is fine. 37 is fine. Then you are getting 43. That should be between 37 and 48. That is fine. So this is absolutely fine. So B is the correct answer, my dear friends. B is the proper probe sequence when you are searching for 43 in a binary search. What about C? There may be multiple options correct, my dear friends. There may be multiple options correct. You have to see that. Don't blindly say B is the final answer, because nowadays we are also having MSQs. Be careful. You started with 81, so obviously next number should be less than that. Then next than that is possible. So any number between 61 and 52 only. Then 14. 14 means it's wrong, na? How 14 is possible after this? Acha, 14 is possible. Sorry. 14 is possible. I'm sorry. We are not in this direction. Sorry. let me put this properly here. 81, 61, 52, 14 is possible because 43 is between 14 and 52 possible. Then 41, that is also possible. After 41, 43 is also possible. This is possible. C is possible. CD options are same, huh? Oh, we created with a lot of effort, so it happened like that. Lot of effort has been done, because of that both options are same, my dear friends. Sorry for that. Okay, you write 45. 45, does it work? Sometimes efforts. 45 if I do it, after 41, 45, after 45, 43, that is fine. Yeah. Now let us see the next problem. The following numbers are inserted into an empty BST in the given order. That is in this, yeah, 10, 1, 3, 5, 15, 12 and 16. They are inserted in this particular order only. What is the height of binary search tree, my dear friends? Please answer this question. Three is the height. So just start inserting, sir. First you can insert 10. After that 1 is less than this. 3 is less than 10, greater than 1. Then 5 less than 10, greater than 1, greater than 3. Then 15 greater than 10. Then 12 greater than 10 but less than 15. 16 greater than 15. So height is 1, 2, 3. Height is 3, my dear friends. So height of this BST is 3. Very good. Height of this BST is 3. Very good. When searching for the key value 16 binary search tree, nodes containing the key values 10, 20, 40, 50, 70, 80, 90 are traversed, not necessarily in the given order. How many different orders are possible in which these key values can occur on the search path from root to the node containing the value 16? How many different possibilities are there? See, we are having these nodes or these keys but not in the given order. How many orders of these numbers are possible when you are searching for the 60? See, for example, you see, when you are searching for 43, these three are possible. So for these numbers, he is asking how many such orders are possible. He is asking for these numbers, how many such orders are possible. He is asking. C7. What is the answer for this problem? 128. See, we are searching for 60. The numbers given are 10, 20, 40, 50, 70, 80, 90. See, my dear friends, you got 129. Oh, torpedo says A, so let us see this. Okay, look here, sir. When you are searching for 60, these numbers 10, 20, 40, 50, whatever they are there, you will be getting them in increasing order or decreasing order, because all the four numbers are occurring. All the four numbers are occurring, correct? So they should appear in increasing order. These numbers should appear in increasing order, because after 20 you cannot get 10. So increasing order only we should get it. This 10, 20, 40, 50 should be occurring in this order, because these four numbers are occurring means they should appear in the increasing order only. They should appear in the increasing order only. Whereas 70, 80, 90 means 90, 80, 70 should occur in this decreasing order. This is what should happen, my dear friends, because these numbers should occur in the 7 positions what you are having, total 7 positions, 1, 2, 3, 4, 5, 6, 7, because 7 numbers followed by 60 you are going to get. See, before 60 you should get all these numbers, means you should get these 4 numbers in increasing order, and you should get wherever they are, they should be in the decreasing order. They should appear in the decreasing order, because first 90 should come, after that 80 should come, after that 70 should come. But where it should come, 90 can come here, 80, 70 can come here, no problem. Am I clear? That is the idea, my dear friends. So what we need to do here is, first identify 4 positions for select 4 positions for this 10, 20, 40 and 50. You have to select 4 positions out of 7. How can you select 4 positions out of 7, sir? 7C4 ways. Suppose 10 here, 20 here, 40 here and 50 here. So remaining 3 positions, select 3 out of 3 positions for 90, 80, 70. So that can be done in 3C3 ways. So this can be done in 7C4 into 3 ways. 7C4 is nothing but 35. So there are 35 such orderings possible, which is option A, correct one. Who says torpedo? You are correct, sir. Torpedo, you are correct. 35 such orderings are possible. Okay, there are 35 such orderings possible. Hope you understand. Is the idea clear? It's a GATE question only. See, my dear friends, these numbers, whenever in the search path from root to when you are finding, you should get them in increasing order. You should get them in increasing order. Whenever you are going to get, you should get them in increasing order only. Am I clear? So 10, 20, 40, 50, they should appear in the same order. No need of arrangement. No, we are just selecting the 4 positions for them, not arranging them. So you have to select 4 positions for them, then 3 positions out of remaining fellow. So these 7 to be arranged, but you are not arranging, sir, just selecting positions for them. So whenever these numbers comes, they should be in decreasing order. Sorry, increasing order, these 4 numbers, and these 3 numbers must be decreasing order. So first 90 should come, then only, because 60 is there, no, 90, 80, 70, then 60 should come. So that decreasing order should be always there, my dear friends. That decreasing order should be always there. For this 90, 80, 70, decreasing order should be there. For 10, 20, 40, 50, increasing order should be there. So what happens? This particular sequence can give you the answer for that. Hope you understand. Is the idea clear? So that's why we are selecting 4 positions for them in 7C4 ways. Once it is done, 3 positions are vacant. 3 numbers need to be filled. That can be done in only one way, that is 3C3 or 1. That is the answer. So let us take up some interesting question on AVL trees. Find minimum number of nodes in AVL tree for a given height 6. Find minimum number of nodes in AVL tree for a given height 6, my dear friends. For a given height 6, find minimum number of nodes in AVL tree. See, my dear friends, okay, B answer, very good. See, the minimum number of nodes in AVL tree for height h is given by the formula nh minus 1 plus nh minus 2 plus 1. This is a formula. So you can just create this particular table for this, my dear friends, which can give you the answer quickly. So height and number of nodes. Height 0, then it is 1 node, because minimum we expect 1 node. Actually empty AVL tree is also there, but generally for this the node should be there, so they take it as 1 here. For height 1, the minimum number of nodes are 2. These are the base conditions for this. For this recurrence relation, these are the base conditions. N0 is equal to 1 and N1 is equal to 2. And from 2 onwards, you can just calculate sum of these 2 plus 1. 2 plus 1 plus 1, that is 4. Then 3 means 4 plus 2 plus 1, that is 7. 4 means 7 plus 4, 11 plus 1, that is 12. 5 means 12 plus 7, 19 plus 1, that is 20. 6 means 32 plus 1, that is 33. So for the height 6, what is the height, my dear? I mean, for the given height 6, what is the minimum number of nodes, my dear friends? 33. 33 is the minimum number of nodes. 7 also let us calculate, which is 54. 8, it would be 87, 88. So these are the other numbers. For height 7, it is 54. For height 8, it is 88. Very good. Suppose we start with an initially empty AVL tree and then insert the keys 4, 3, 2, 9, 6 in that order. Using the insertion algorithm with rebalancing, what would be the pre-ordered traversal of the resulting tree? After you insert this 4, 3, 2, 9, 6 in that order using insertion algorithm, okay, of AVL trees. You know, AVL trees, the rotations we have to do for balancing, LL rotation, RR rotation, they are called single rotation. We have LR rotation and RL rotation, which are called double rotations. Okay. So let us see this with this example, my dear friends. So we are inserting 4, 3, 2, 9, 6. See, the idea is we just insert as we insert in your binary search tree only. Only thing is, once there is a balance out, based on where the insertion happened with respect to the fellow whose balance factor is different. See, balance factor means the height of left subtree minus height of right subtree. It should be always less than or equal to 1. That is, the balance factor should be either -1, 0 or 1. Am I clear? So let us start this, my dear friends. So first let us insert 4. So when you insert 4, no problem. Then 3 is inserted in the binary search tree. Because 3 is less than 4, you insert it on the left. You insert it on the left. Then 2 is inserted. So it is 2 here. Now with this, what happens? The balance factor will be lost. Here it is 0. Here it is left subtree. See, height means the including this edge also you are going to calculate, sir. So the height is 1 here. Right subtree is 0. So here it is +1. But here it is left side 2 edges, right side 0. So here the balance factor is 2. So there is a balance problem, and that is due to insertion of a node in the left of left subtree. So here we are going to do the LL rotation, my dear friends. Here you are going to do the LL rotation, my dear friends. So when you do LL rotation, what happens? Just 3 will go up, 4 will be the right subtree, and 2 will be the left subtree. So once it is done, now balance is happy balance. Now what happens? Insert 9. 9 is greater than 3 and greater than 4. 9 is, okay, let us do it in the next step. So after this, we are inserting 9, 3, 2, 4, 9 is inserted, no problem. Then 6 is inserted. 3 is greater than, 6, you are inserting 6 now. 6 is greater than 3, greater than 4, and it is less than 9. So 6 will be on the left subtree. But because of this, there is a violation at the balance factor here. The balance factor here becomes -2. And this is due to the insertion of a node in the right of left subtree. It is due to the insertion of a node in right of left subtree. So here we are going to do RL rotation, my dear friends. Here you are going to do RL rotation. See, RL rotation, first you can do LL rotation followed by RR rotation. That is with 2 fellows you can do it. I'll just show you 2 fellows. See, first you can do like this, 3, 2, 4. Here you can do this LL rotation first. First you can do LL. LL means what happens, sir? 6 will come up and 9 will go. Then you can do RR rotation. Then you can do RR rotation. So it is 3, 2. Then when you do RR rotation keeping from here, so it is 6 will come up and 4 will go down left side and 9 will be the left side. Or directly people RL rotation directly what they do, this 6 will come up, this 4 will go to the left subtree, 9 will go to the left subtree. That is also how people do it. 3, 2, 6 will come up, 4 will be the left subtree, 9 will be the right subtree. Whatever method you want, you can follow that, my dear friends. This is using 2 rotations we can show it, or at a time you can show it, my dear friends. Whatever way you feel preferable, you can follow that method. So this is called RL rotation. Now after this, what is the pre-order traversal, my dear friend? What is the pre-order after this, my dear friends? So the pre-order is, pre-order means what? First root, then left, then right. So first 3, then left, then root, then left, then right. That is 3, 2, 6, 4, 9 is the pre-order. 3, 2, 6, 4, 9, which is option C. So Nayak, you are saying 2 is the answer, but that is not the correct answer. I said pre-order, na? Nayak, is that okay? So for this, 3, 2, 6, 4, 9 is the AVL pre-order for the AVL tree, my dear friends. Yeah, C is the correct answer. C is the correct answer for this, my dear friends. Hope you all understood this. No problem, sir. No problem. Suppose we start with an initially empty AVL tree and then insert these keys 2, 1, 5, 4, 3 in that order, followed by deletion of the keys 5 and 1 in that order using deletion algorithm. What would be the pre-order traversal of the resulting tree? No problem, sir. Please correct your mistake. That's it. Dare to do mistakes, care to correct it. 4 and 3. So again, story is the same. We are having this particular keys insert into initially empty AVL tree. After inserting, you have to delete 2 keys. So first let us do the insertion. First 2 is inserted. Insert 2. So 2 is inserted. Insert 1. So 1 is smaller than 2. Insert it. Then insert 5. So 5 is larger than 2. So inserted on the right side. Then insert 4. So 4 is actually greater than 2 but less than 5. Then finally insert 3. So when you insert 3, actually 3 is greater than 2, less than 5, less than 4. And because of this, there is a balance factor violation, which is +2. And this happened due to the left of left some insertion is happened. Left of left some insertion is happened. So you just do the LL rotation, my dear friends. You just do this LL rotation, my dear friends. That is 2, 1. So what is LL rotation? 4 will move up, 3 is here, 5 is here. And after LL rotation, this is what happens, my dear friend. And this is your AVL tree with the after insertion. This is AVL tree after insertion. Okay. Then what happens? You need to delete the elements. So just deletion is, if it is leaf node, happy situation. Otherwise, ya to predecessor, ya to successor, you have to delete it, my dear friends. Am I clear? So first you have to delete 5. Deleting 5 is straightforward because it is a leaf node. Happily, the parent link you can make it null. Directly it is removed. No problem. 2, 1, 4, 3. Now you have to delete 1. Again, 1 is also not a problem because it's a leaf node. Just make the parent link null. Delete 1. But after deletion, what happens? Here you are having a problem. Okay. So when you delete this fellow, the balance is out on the right side. The balance is out on the right side. And here you see this fellow is having 0. So it is actually, RL rotation will happen here. RL rotation need to be done here. Just do RL rotation here. Am I clear? Hope you understand. Hope you understand. So because this 0 factor, we call it as L0 or R0. What rotation you call it? So just RL rotation you can do it. Ultimately 3 will go up, 2 will be here, and 4. Just RL rotation only, sir. The naming may be different. Differently they'll give you the names. Like I think it should be L0 rotation they call it. Whatever it is, by directly rotating, you are going to get this answer. 3 to 4. So what is the pre-order for this? Pre-order for this is 3 to 4. Pre-order means 3 to 4. That is option A. Option A is the pre-order for this, my dear friends. Option A is the pre-order for this. Hope you understand. Is the idea clear, sir? Now let us take up some problems on heaps so that we can conclude today's class, my dear friends. Am I clear? See, deletion of root node means you have to find the successor or predecessor, replace that. You don't remove the predecessor root node directly like that, sir. With Tagi, it is same as deletion of a root node in binary search tree. AVL tree deletion is same as deletion of a node in BST. Am I clear? So that is what you are going to do. You are deleting the root node. Means you are not actually deleting it. You are replacing it with its successor, and that node is what is actually deleted. The successor node or the predecessor node is actually what is deleted. Is that clear? Is that clear, Vitishta? So you don't delete the node. See, when it is having 2 children, you don't delete it directly like this. Okay? We don't delete it directly like this. It has to be identified what is the successor or predecessor. What is the successor element? 3. So we actually, in this case, suppose if you are having this, say 2, 1, 4, 3, 5. If you want to delete it, the successor of 2 is 3. So you swap 2 with 3, 2 comes here. Now that fellow will be having either leaf node or it is having single child. That can be deleted, my dear friend. So now 2 can be happily deleted. So this is what happens after deletion of root node here. This is what happens when you delete root node. So you get 1, 3, 4, 5. This is what you get it in this case. Am I clear? In the right subtree, leftmost child will be the successor. Like that you can do it. Yeah. Now heap. What is the heap, sir? So heaps are maintained in the array in level order. And here what happens, sir? At index I, whatever element is there, 2i is its left child, 2i plus 1 its right child. When it is a max heap, the value at root node is greater than or equal to its child nodes. That is the idea, my dear friends. So just with a 2i plus 1 you can find left and right child, my dear friends. Similarly, the parent of any node is I by 2, floor of that can give you the parent of any node, my dear friends. It's a very straightforward thing. Which of the following is binary max heap? Which of the following is binary max heap, my dear friends? Option A is binary max heap. A and C. Which of them are binary max heaps? You have to identify them, sir. See, option A, when you take it, just draw. See, it's always to draw that and see that particular diagram. It is easy for you, sir. So first let us draw that 25. Level order you draw 25, 12, 16, 13, 10, 8, 14. See here, this 13 is larger than its child, therefore it cannot be max heap, sir. 13 is larger than its parent, that is wrong. So option A is wrong. Option B, 25, 14, 13, 16, 10, 8 and 12. Okay. Now when you consider this, here 16 is larger than its child, 16 is larger than its parent, that is wrong. This is wrong. So B is also not a max heap. Let us see option C, 25, 14, 16, 13 is smaller than 14, 10 is smaller than 14, right? 8 smaller than 16, 10, 12 smaller than 16. So this is the correct answer. C is the correct answer. C is the correct answer. What about D? I am writing D here. 25, 14 is smaller than 25, 12 is also smaller than this. Then 13 is smaller than 14, 10 is also smaller than 14. 8 is smaller than 12, but 16 is not smaller, so failed. So only C is the max heap, my dear friend. Only C is the max heap, my dear friends. Only C is the max. Yes, 16 is larger, therefore it is failed. So D option is also not max heap. Only C option is max heap, my dear friends. See, similarly, similar to max heap, we can also have min heap. Min heap means the value at the root node must be larger than its children nodes. That is min heap property, my dear friends. Hope you all understood. See, there are two ways of constructing max heap. One is directly from initially empty max heap, keep on inserting the elements into max heap, which takes actually order n log n time. My dear friends. Whereas if you can create the array, from the array if you convert into max heap, it can take order n time, my dear friends. It will take order max heapify procedure, you call it. So here the first problem is, this particular problem is asking you to insert one by one in the given order into a max heap. Then what is the max heap? So you have to insert these elements one by one into a initially empty max heap. So let us see 32, 15, 20, 30, 12, 25 and 16. Now some people joined. Right? Got it. Wonderful. So now what happened? 32 is inserted. After that, that is in the level order, you have to insert the element. 15. Now because it is a max heap, is max heap property satisfied? If it is not satisfied, you have to move that element up till the root. You have to move that element till the root node, my dear friends. Then after that what happens? 32, 15, then 20. 20, the condition is satisfied so far. 32, 15, 20, then 30 is added. Now here there is a violation in the condition because the root node should be larger than the child node. So here 30 is moved up and 15 will be here. Again this is to be compared with its root node, because after this swap don't stop there, because that may be larger than its root node. Check that. But here no problem. So that is fine. That is fine. So after this we are inserting, after this what is that? 32, 30, 20, 15 is inserted. Now 12 is inserted, not a problem. After that 32, 30, 20, 15, 12, then 25 is inserted. Now there is a problem. So swap, 20 comes down, 25 moves up. Anywhere else it will move up? No. So that is where it stops. Wonderful. So it is 32, 30, 25, 15, 12, 20. After that what happens? Because 25 is done, finally 16. It has no problem, my dear friends. It is having no problem at all. So now you can arrange them in the order, that is 32, 30, 25, 15, 12, 20 and 16. So this is the correct order, my dear friends. That is 32, 30, 25, 15, 32, 30, 25, 15. Up to here they are all same. This is wrong. This is wrong. 12, 20, 16. 12, 20, 16. 12, 16, 20. Therefore it is wrong. Option A is correct. 32, 30, 25, 15, 12, 20, 16 is the correct answer. That is option A is the correct answer, my dear friends. Option A is the correct answer, my dear friends. Got it? See here how many swaps happened, sir? That also they can ask you. 1, 2 swaps, number of swaps or number of exchanges happened. Number of exchanges happened is equal to 2. That they can ask you, sir. That question also they can ask you. Next one, the minimum number of interchanges need to convert array into a heap with maximum element at the root is what? The minimum number of interchanges needed to convert the array into a heap with maximum element at the root. So this is the array, directly array is given. You have to convert into heap. So let us see this. 89, 19, 40, 17, 12, 10, 2, 5, 7, 11, 6, 9 and 70. So this directly array is converted to heap. So what happens? First of all, let us create the level order tree for this. 89, 19, 40, 17, 12, 10, 2, 5, 7, 11, 6, 9 and 70. See how many elements are there, sir? 3 plus 4, 7, 7 plus 4, 11, 13 elements are there. So 13 by 2 means 6. So actually 6th element onwards you need to consider, because 7th element onwards it will not have any children. You see 7th elements onwards you don't find any children. So 6th element onwards you have to do the heapify procedure. 6th element onwards you have to do the heapify element. Means it has to be compared with its parent. So that need to be moved up to the root node, my dear friends. That need to be moved up to the root node, my dear friends. Sorry, it need to be moved down, not moved up, moved out. So you have to compare with its children whether the heap property is satisfied or not. If heap property is not satisfied, this element will move up. Again that will be compared with, because whenever an element comes up, it has to be compared with its parent, my dear friends. So now with 10 what happens? There will be a swap happens, because it is max heapify you are doing. So 70 and 10 will move down. it cannot go any further down, you can stop it here. Am I clear? It can stop it here. Now next element, it is fine with its children, no problem. Again 17 is compared with its children, not an issue. Then 40 is compared with its children. See, 40 is smaller than its children, so 40 and 70 are swapped. 40 and 70 are swapped. 40 comes down, 70 moves up. Again this 40 need to be compared with its children, no problem, so it stops there. So this finally completed. Now 19 is fine because 19 is larger than its children. Then 89 is fine because it is larger than its children. So how many interchanges happened, sir? Number of interchanges happened. The number of interchanges happened is equal to just one interchange and two interchange. Two interchanges you converted this fellow into, with just two interchanges you converted this into what, sir? Max heap. That's it. That is a max heap. Hope you understand. Clear to you all? Now, what is the content of the array after deletion of two maximum elements from max heap? See, most of these algorithms, like Kruskal's algorithm, okay, in all these problems, like even in Dijkstra's algorithm, you maintain this max heaps or min heaps, my dear friends. Min heaps you are going to maintain. So the next minimum elements you have to remove. Here I said max heap. There you use min heaps. That's it. The story will be exactly same, my dear friends. Story will be exactly same, my dear friends. Please remember that. Hope you understand. What is the content of the array after deletion of two maximum elements from the max heap? 25, 14, 16, 13, 10, 8 and 12. So here we are having this max array. Am I clear? So when you draw this, this is 25, 14, 16, 13, 10, 8 and 12. See, whenever you want to delete any element, whenever in the max array or max heap or min heap, if you want to delete element, you have to swap this fellow with the last element. You have to swap this fellow with last element. That is 25 has to be swapped with 12. So 12 will come up and 25 will go. Now you are going to heapify this element. You have to do the heapify here, my dear friends. But only up to here. That is, last element need not be considered, my dear friends. So when you do heapify, what happens? 14 and 16, 16 should come up and 12 should go down. 12 again compared with 8, because right side element you cut this problem here itself. Okay, so 12 is here. So after this, what happens? You get 16, 14, 12, 13, 10 and 8. You see, next maximum element is at the root. Next maximum element is at the root. Now again you want to delete 16, means what you have to do, sir? 16 has to be swapped with the last element. So 16 comes here, 8 comes here. You have to do heapify here. You have to apply the heapify algorithm. So 8 is compared with 14 and 12. So 14 comes up, 8 goes down. Again 8 is compared with its child nodes. 13 comes up, 8 will go down. So after this procedure, what happens? 14 comes up, then 13, then 12, then 8, then 10. Because this is done, we cut it here, my dear friends. Because this 16 is removed now, we cut it here, like that. So this is the idea, my dear friends. So this is what happens after you delete two elements. Okay, so it is 14, 13, 12. Which is the correct option? What is the correct option here, sir? What is the correct option here? 14, 13, 12, 8, 10. Correct. 8, 10 or 10, 8, sir? Because 8 has to be swapped with 13, na? 8, 10, not 10, 8. D is the correct option. Okay. So this is about your, data structures on tree problems, sir. So I completed tree problems today. Okay, I am going in the air. So let me bring me down to my position. Fine. Right. Now look at this, sir. We are having this different series. 1 second. Yeah, Rakesh Talreja sir is coming up with this. Rakesh Talreja sir is coming up with this general aptitude session very soon, coming soon. 15 marks just in 15 hours. So you can make use of this particular session to score maximum marks in aptitude. Then again, Talreja sir as well as Ankit Joshi sir are coming up with, maths marathon series. So our discrete mathematics may be conducted in connection with this only. So or separately I'll plan it and will let you know accordingly, my dear friends, because for computer science students not all the topics are available, only the 3 topics: calculus, linear algebra and probability. Okay, so after that we can do our discrete mathematics topic, right? So that is the idea there. And we have this particular test series uh, conducted by our BYJU'S Exam Prep. You can access this particular test series for very nominal fee, and this is having very good features. You can make use of this to get maximum score, and you can also see this or use this particular test series to understand your mistakes, where you are doing mistakes. To overcome those mistakes, you can utilize this particular test series, because there is a detailed analysis of this particular test series is done. Okay, so what mistakes you are doing, in which areas, all this analysis will be provided to you. That is the unique advantage of this test series, right? And that's about today's class, Babu. And tomorrow when we meet, we'll see this linked list, stacks and queues. If any other topic, please let me know. Otherwise, those are the 3 topics with which our marathon series will be concluded from my side tomorrow. Right? Thank you, sir. Have a nice day. Okay, prepare well. The last few days, don't lose your hope. Okay, hashing also will be done tomorrow. Hashing also will include tomorrow. Okay, we'll solve problems on hashing also tomorrow. That's all for today. Thank you. Good night or good morning, good evening, good afternoon, whatever. Right.